Isn't RF communication a very cool technology where it's possible to send packets of data without any physical connection? There are many RF modulation techniques out there, but LoRa is the trend nowadays. Today in this video, we are going to use RYLR998 LoRa Module to let two STM32 MCUs communicate over LoRa. And we are going to design a simple protocol and call it Useful LoRa or ULoRa. So without any further ado, let's start our video. Alright, so let's start with our MCU configuration. As you may have noticed, since we are dealing with the new MCU, STM32 F411, the IC package has changed, and of course now we have a lot of new peripherals to discover. So yeah, prepare yourself for more interesting content in the future. Now let's continue with our topic and have a look at the LoRa module datasheet that we are going to interface today. So here we have the module name, RYLR998. I suppose that it refers to RYLR LoRa. So I will be calling this module RYLR LoRa Module during this video. This module is interfaced over UART using AT commands. And here we have the operation frequency. And yeah, now let's have a look at the pinout of the RYLR LoRa module so we can set our MCU accordingly. So first of all, we have the VDD supply pin. I suppose that it's connected to 3.3 volt as far as I remember. Yeah, exactly. And after that we have the reset pin. This pin can be either connected to our MCU to an output pin, because this is an input pin, or it can be pulled up to 3.3 volt, and it already has pull-up resistor, 100 kilo ohm resistor, and of course the UART pins, RX and TX, and at the end we have the ground. So let's get back to our MCU and set our pins accordingly. So as you can see, I've configured the UART at these pins. Let's have a look at its configuration. So this is the default baud rate of the RYLR LoRa module, and we have the word length is 8 bits and no parity with one stop bit. So it's quite standard. Even if you have another CPU like ESP32, you won't be having any problem interfacing this module. And we can see the UART related information just over here. And the module reset pin is connected to pin B14 to my hardware. So I'm going to set it as output and give it a name. There's also an onboard LED that we can make use of in our project, connected to PC13 pin in sync mode. So in order to use this LED, this pin will be reset. We have also a push button connected to A0 as far as I remember. Yeah, here it is, and it's active low. So yeah, let's configure these pins accordingly. There is one thing I want to point out here. The push button does not have a pull-up resistor, so we need to activate the internal pin pull-up resistor so we can read the status of the button properly. And of course the button pin will be set to be external interrupt falling edge trigger. So let's activate that. I think now we are ready to generate our code and start programming. Alright, so CubeMX has generated our peripherals initializations. So to start with, I've written few functions in order to test our module, the RYLR LoRa module. And of course we start with enabling the module by setting its reset pin, and we see that over here is just a GPIO set function. And we see this piece of information in the module document just over here. So the reset pin should be set before starting transmission or reception. So let's get back to our code and let's close this. And yeah, so let's get back to our main and carry on. And for the sake of testing the module and the communication with the MCU, I've written this piece of code. So every second, a test AT command is sent over UART. To have a full understanding of AT commands, let's take this AT test command as an example. So in order to let the module understand the command that we are sending, the command should be terminated with carrier and feed line characters. And the module will respond with OK, so we can make sure that the communication is OK. Quite convenient. So let's see how this should be implemented on our code. So first we see the transmission buffer is initialized with 4-byte storage, and then 80 characters are loaded to the buffer. After that, these characters are concatenated with the terminator characters, the ones that we were talking about before. And then the transmission starts here. So now let's see how this appears on our logic analyzer. Alright, so far so good. In this side we see what we have transmitted, the 80 and the terminator characters. And we see the response of the RYLR module just over here. It answers with OK, and the terminator characters started with plus character. I suppose every response will start with this character. So knowing this, we can have an idea when the response starts and when it ends. Alright, so before implementing a complete driver to control the module that we are going to use today, RYLR998, let's have an overlook over the 80 command guide. Alright, so let's start with the basics. 80 address command is used to set the address of the module, and every module should have a specific address because it's necessary for transmission and reception. 80 network ID is used to specify the network that the module is going to communicate through. So in order to transmit a specific packet of data, both modules, the receiver and the transmitter, should be at the same network. And the transmitter, of course, should know the address of the receiver. And 80 band command is used in order to specify the frequency band that the communication is done over. There are typical frequency bands that LoRa communication is done over, and we will cover this in just a minute. Actually, all these parameters are necessary in order to have a successful communication. So let's have a look at the parameters that should be sent along with these commands. And let's start with module address set command, and we have it right over here. So in order to set the address of the module and send the command over UART, the command is appended with equal sign, and then the address is added to the whole command. And pay attention that the address should be in ASCII, so every digit will be one single byte. So here we see a complete example of the address set command sent by an MCU. And of course, we should not forget the carrier and line feed characters appended to the packet. And of course, when the module receives this packet, it will answer with plus character and OK, appended with carrier and line feed as well. This of course will change the module address permanently until this command is sent again with different address. In order to read the address of the module, the same command can be sent appended with question mark, and the module will be answering this way. So now let's have a look at the implementation of such command in our code and go through it step by step, because implementing the rest of the commands is quite similar to this one. So first of all, we see the set address function takes a pointer to the address as a parameter, and in the function body we see the transmission buffer is first of all loaded with 80 and plus characters, and then it's loaded with the address word. After that, concatenated with the equal sign, and then the address passed to this function is appended to the buffer content. And at the end of the day, the buffer is terminated with carrier and line feed characters. And now our buffer is ready for transmission. UART pooling transmit is used to transmit this command. It's not an efficient way, but for testing purposes, I'm using this one. In the upcoming video, I'm planning to improve this code and make it more efficient, like using DMA instead of pooling method. So stay tuned for that one. Notice that I'm only considering one digit for the address. This is enough for me. I only have 2 modules to deal with, so it's okay for now. Note that the rest of the commands will be handled the same way. It's full of appending and concatenating, so the rest of the commands will be easy for us. Alright, so now let's have a look at address get command. It's also handled in a similar manner, but the only difference here is that instead of concatenating equal sign, question mark is concatenated after address word, and then the terminator characters are concatenated, and then the transmission takes place. Remember that in this case we need to know the response of the module so we can determine its address. That's why UART receive interrupt is activated here, with a size of 12 bytes. So once we receive this amount of data coming from the module, this interrupt will take place, and the data will be stored in the RX buffer. So now let's see how all these commands should be executed in practice. First of all, the module reset pin should be set to 1, and we have it over here. And then we have a delay. Usually I don't like HAL delay because the CPU gets locked, but this for test purposes. And then address get command is sent to the module. And then in the while loop, when the interrupt flag is activated, and we have the interrupt is activated inside the reception complete callback, it's activated right over here. And now we know that the data is received and it's stored in the reception buffer. And now we can parse this data and get the information that we want, like the module address. But of course, we should not forget to disable the interrupt flag so we don't access this condition again. So let's have a look at the parser over here. So in the packet parser, first we check the first byte of the received command, whether it's plus character or not. And in order to determine what the command is, we compare the received command against a macro that we know its result before. So it's either like address, or receive, or OK, or even some other command like getting the bandwidth, network ID, or any other parameter. And then depending on the comparison result, we return that to the parser function. And depending on the determined command, we take an action, and we see this over here. So let's take address command as an example. Say that we are asking for the address and the module is returning the address to us. And we already know that the address information starts at the 9th index of the received packet, and we see this just over here. So we check if the received address is not 1, we force it to be 1, and then set address command is sent to the module. Of course, during this procedure, we should not forget integer to ASCII and ASCII to integer conversion, because all the commands related to the module are done in ASCII, so this is quite important. So we should take this into consideration every time we are sending or receiving data from the module. So now let's see how this address getting command is done in practice. So let's have a look at the signals read by the logic analyzer. So here we see both the UART RX and TX lines analyzed by the logic analyzer. First we see our MCU is sending address get command, and after a bit the LoRa module answers with its address, which is 0 in this case, and we see this over here. And once the reception is completed by our MCU, an interrupt is triggered and it sends set address command with address 1, just like we have intended in our code. And after a bit of time, the LoRa module answers with OK, confirming that the command is valid. So now let's have a look over the rest of the 80 commands provided by the LoRa module and review them quickly. 80 parameter, on the other hand, is used in order to set several parameters in order to determine the performance of the module. So for example, increasing the spreading factor will increase the reception quality at the receiver side, but the transmission time will be much longer. And also, having a smaller bandwidth will also increase the reception quality, but the transmission time will be also much longer. So as you can see, there is a trade-off when it comes to customizing these parameters. And we have here the coding rate. Coding rate is used to check the integrity of the received packet. And last but not least, we have the preamble code. Less preamble code value will lead to packet loss, and the recommended value is anything above 10. So let's stick with that. And here we have the recommended set of the 80 parameter command. Now let's have a look at its format. Here are the values and the parameters that you can modify. Personally, I'll be sticking with the recommended values, so I won't be messing with any of these numbers. So let's have a quick look at the rest of the commands. So first of all, we have 80 test command. We have already done this at the beginning of the tutorial. And then we have 80 reset command in order to reset the LoRa module. 80 mode set. So there are 3 modes to choose from: transceiver mode, sleep mode, and smart receiving power saving mode. So these options can become quite handy if you have some power related concerns or your module is connected to a battery. And here we have baud rate set command. The default options is the fastest one, so it's logical to stick with it. We have here the parameter set command and the band set command, where the communication takes place. Set address command, we have covered that. Network ID set, we have several networks IDs to choose from. And here we have RF output power set command. There are 23 options to choose from. This is also range to power trade-off option, so this also can be considered. And here we have send command and receive command. These are the most important commands, so let's focus on them. So in the AT send command, first the address of the receiver is selected, and then the length of the sent data is determined, and then the payload is loaded to the command. This command can send up to 240 bytes to the receiver in one shot, which is quite nice. And in the receiver side, it's not actually a command, but some sort of a response. So once the module receives the transmitted data, it will respond to the MCU with this packet. So it responds with the transmitter address and the length of data, the payload, and the received signal strength indicator, and the signal to noise ratio. So here my plan is to design a simple protocol, and this protocol will take place within the data packet. So I can send several commands to the receiver to do several actions. So I have actually designed 3 packets, and they are not acknowledgement, acknowledgement, and connection test packet. So every packet will have its own packet ID, packet size, and this packet will contain the number of modules within a network and the checksum of the whole packet. So we can make sure that all the data inside one packet has been received without any problem. So let's have a look at the code implementation. Here we see that I've set a timer, a software timer. So it sends the connection test packet every 1 second. So now let's have a look at the content of the send function. Here we see that depending on the command passed to this function, the data and the payload length segment are filled accordingly. And here we see the communication test packet is filling the transmission buffer. Overall packet size calculation is done, and then the transmission buffer is filled with command characters. And right before transmission, integer to ASCII conversion is done, and then the transmission takes place. Alright, so now let's see how our send command will appear on the logic analyzer. So as you can see, I've set the MCU to send AT send command every 1 second to the module, and if we zoom in, we see first of all the command context, and then the receiver address, the number of bytes sent by the transmitter, and then the connection test command that we have discussed. So here we see the packet ID, the packet size, the number of devices in the network, and the checksum. There's actually one thing I forgot to mention here. Notice that there's a comma between every packet segment. It is necessary for the module to separate between parameters. So keep that in mind, and once the complete packet is transmitted to the module, we see the module answers with OK after an amount of time, and it's around, here we have a look at it, it's around 168 milliseconds. So now let's have a look at the receiver side and see how things are going on. So here we see on the UART RX line, the packet is received every 1 second, just like we have transmitted it. And when zooming in, we see the receive command containing all the data that we have transmitted. So here we have the source address, which is 2, the number of data 4, and the communication test packet. And here we have the RSI -17 and the SNR parameter here. Nice like a dice. Okay, so let's see how this packet is handled at the receiver side. I've written a simple sketch that receives the data over UART interrupt and store it inside a buffer in the RAM. And in order to check if the data is valid, we use the checksum that we have transmitted. And if everything is fine, an onboard LED is turned on for 300 milliseconds and then it's turned off. So let's see how this works in practice. Alright, so right now you can see the black pill is communicating with blue pill over LoRa, and every 1 second the black pill is sending a packet to the blue pill, and when the blue pill receives the packet, the LED is turned on for 300 milliseconds, and we see the communication is going on without interruption. So I can stop the communication when resetting the black pill. Let's see how it works. So as you can see now, the green LED is not blinking anymore. So now we see the communication coming back. Yeah. The distance right now is quite close. I suppose that this is not the right way to test the modules. They are supposed to be tested at long range because this is the LoRa feature. So in the upcoming video, I'm planning to do both range test and power consumption test. So stay tuned for that. So now I've written a simple sketch to the black pill board, to the transmitter side. So when the key button is pressed, the LoRa module will transmit a packet to the receiver side, to the blue pill side. And on this side, again, the green LED will be turned on. So every time I press the button, we see the packet is transmitted and received by the other side. This brings me to the end of this tutorial. If you have learned something new, please share this video among your friends and let them know about useful electronics. Stay tuned and bye-bye.